trust is the currency of modern software development. When you install a package, you are handing over the keys to your digital infrastructure. Recently, that trust was shaken in a significant way involving the LiteLLM project. Versions 1.82.7 and 1.82.8 on the Python package index were compromised. This is not just a bug. It is a supply chain attack that highlights the fragility of our current dependency model. For data scientists and tech leads, this incident is a stark reminder that the tools we use to manage artificial intelligence can themselves become the attack vector. To understand the gravity, we must examine what LiteLLM does. It acts as a proxy between your application and various large language model providers. It abstracts the complexity of different application programming interfaces into a unified interface. When you add this tool to your environment, you are essentially creating a gateway. The compromised versions introduced a malicious file named LiteLLM init.pth. This is a specific Python mechanism that executes code automatically upon import. Unlike a standard script that runs when you call a function, this code runs the moment the library is loaded. The payload itself remains a subject of investigation. Some reports suggest it was a sophisticated credential stealer. It was designed to harvest secure shell keys, cloud credentials, and cryptocurrency wallets using advanced encryption standard 25/6 encryption. Other accounts indicate the payload was a base 64 encoded blob within the proxy server file, designed to cause RAM exhaustion through a fork bomb. Regardless of the specific mechanism, the consensus is clear. The primary attack vector was the unauthorized modification of the package upload process. Attackers successfully impersonated a maintainer to release these malicious versions. This breach was detected in an unusual way. It was not traditional security scanners that flagged the issue. A model context protocol server, a system designed to give context to artificial intelligence models running in a development environment, inadvertently served as an early warning system. This highlights a paradox where modern AI-assisted workflows can inadvertently expose supply chain attacks. The incident underscores a critical vulnerability in the Python package index upload process. Even popular open-source projects with large user bases are susceptible to rapid credential theft and credential stuffing. Now consider the architectural implications. For tech leads, the danger extends beyond the immediate compromise of a single repository. When you rely on a proxy layer for your artificial intelligence infrastructure, you are creating a single point of failure. If that proxy is compromised, the cascading failure risks are severe. Imagine your application routing sensitive queries through a gateway that has been turned against you. The proxy could exfiltrate prompts, inject malicious instructions, or simply become unavailable when you need it most. This is a cascading failure because the compromise of the infrastructure layer directly impacts the application layer above it. The response from the LiteLLM team has been swift. They rotated all maintainer accounts and revoked credentials across GitHub, Docker, and the Python package index. They engaged Mandiant for forensic assistance. Users of the official Docker image remain unaffected as they pin dependencies locally. However, knowledge gaps persist regarding the full extent of the breach timeline. Whether the fork bomb and credential stealing reports describe sequential phases of a single attack or conflicting initial assessments remains unclear. This uncertainty is dangerous. It means we cannot assume the attack stopped where we think it did. This brings us to the core of re-architecting for resilience. We cannot rely solely on the security posture of a single vendor. We must design systems that assume compromise. The first step is immediate credential rotation. If you installed the compromised versions, you must revoke all application programming interface keys associated with affected environments. This is not a suggestion. It is a requirement. You should downgrade to version 1.82.6 or earlier. The malicious code persists in the compromised versions and may have already exfiltrated sensitive credentials. Beyond the immediate fix, we need to think about vendor-agnostic safety. Relying on a single proxy for all your model interactions concentrates risk. Consider implementing a strategy where critical operations can fall back to direct API calls if the proxy layer is suspected of compromise. This adds complexity, but it reduces the blast radius. You want to ensure that if the gateway falls, your core data does not follow. Furthermore, we must look at how we verify our dependencies. The Poison security scanner suggests that automated dependency checks and security tools can be manipulated to bypass detection mechanisms. We need to diversify our verification methods. This might mean using multiple scanning tools that do not share the same dependency chain. It might mean implementing strict pinning of dependencies in your continuous integration and continuous deployment pipelines so that unexpected updates cannot slip through. The incident also highlights the importance of runtime monitoring. Since the attack was detected by a model context protocol server, it suggests that monitoring the behavior of your dependencies in real time can catch anomalies that static analysis misses. If a library begins accessing network resources it normally does not, or if it starts consuming memory at an abnormal rate, that is a signal. We need to treat our dependencies as untrusted until proven otherwise. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.